I'm gonna explain this to everyone just so we can like be on the same page with what to say, even if you know.
Thank you.
Gravity bends light, but it warps space-time, and light is affected by that, essentially moving and bending light. If you go far enough away from the sun, you can observe that light converging to a focal point, and that is where you observe the Einstein-Ring around the sun, and that range is 650 to 900 AU for imaging purposes. With that, theoretically, you can image anything that is reflecting light between 1 to 100 light years away with extreme precision. In our case, we're doing Proxima Centauri b, which is the closest Goldilocks planet to us, and that is 1.3 light years away. With our imaging, we should expect 1 pixel of the planet to be about 10 by 10 kilometers. So extreme precision, enough to see atmosphere, enough to see terrain on the planet. Very useful for observing like the habitability of a nearby planet. Please talk about each of your subsystems. If asked, like, just get into that because that's what you guys are like. That's what we worked on. As for our simulation, we have a GUI set up that will run live synthetic telemetry from each of our subsystems with toggleable results as well as events viewer. Ethan knows what I'm talking about. And most importantly, the image process, not most importantly, but also the image processing is take a picture with this camera of one of these, not one of these, but the bigger planets, wherever they, one of these, and load it into the sim. We have software that will change it into what an Einstein-Ring would look like, containing all of the information within that ring of what we would see in space, and then using fast Fourier deconvolution to turn that ring into a 256 pixel very rough image, and then we use finer like contrast details to expand that 256 into 512 and then fill in those blanks, and then go from 512 to 1024, fill in those blanks, 1024 to 2048, fill in those blanks, and then we build into that 2048 image. So that's how it works, and the output should be, you can see each of those images. We're working on getting TCP connection between the Jetson Nano and the Raspberry Pi. The Raspberry Pi handles the telemetry, the Jetson Nano should handle the image processing. Questions?
I feel media trained.
Good? Media trained?
All right, let's go.
And whatever you do not talk about feasibility. Yeah, no.
Computer sciencey, but which is the reason why we have to sort of restart with the internet system. I think we have to scrap the high fidelity sensor stuff. So we just did this really mad opportunity. And essentially the challenge
It's running.
It's running? Beautiful.
Yeah.
Beautiful.
you want to see with this?
You want to see?
Yeah, I do.
Would give readings for like how far off it is by angle and like what accuracy that is. And then if it needs correction, then this guy would say, okay, we'll run your correction motor to bring it back to alignment and stuff. And it does that for every subsystem. It's like thermal, electrical, for Star Tracker, for everything. And then it also communicates with this guy to say, once we've captured an image, it sends it over to the Jetson, and then the Jetson does the image processing, which is to say that it does fast Fourier transfer deconvolution of the point spot function to deconvolute the Einstein ring to turn it into a 2D image.
So if this specifically like does all of the corrections for all the subsystems, do you have any like redundancy built in? Because this would be expensive to put into space, I assume.
Yeah.
If this fails, then you got nothing else,
Yeah,
right?
yeah, that's why. It's supposed to. It should have. This is just sort of a prototype model, but yeah, you would need a redundancy. Like you need a RAID system for your storage. You would need error correction for memory, and you'd need several of these running in parallel as a cluster, realistically. This is like a single system, but because we're not going to try to build a whole rack of these, especially with prices what they are right now.
How much was it?
Each of them were $300.
Yeah, about 300.
Like it's up there, you have a rack of
and they
these
didn't
things,
want to
1,000.
fund the Pi, so we had to buy it out of pocket.
because we
That's
focused
brutal.
on the
So
front
yeah,
end
but you
early.
would have a redundant convolution to take these images of rings. So see, look, now it's making it right. So first it captures this ring basically, and then it turns it into a really low. Once it does that deconvolution, it turns it into a really low resolution image, and then it looks for regions of interest where there's high contrast. And then it adds refinement in those sections, and it continues to do this up to as high as right now I have it up to 1024, but as far as high as 2048 by 2048.
What you guys used to code it?
C++. Well, yeah, it's mostly C++. The only thing that's not is Python.
Yeah.
But everything else is C++.
What's your project?
And then this is CUDA accelerated image processing, but it's C++ CUDA, not Python. I mean, thankfully everybody wrote their own code for their own subsection and outlined all of their values. So to integrate it all into one code wasn't there.
Yes.